In this section, our goal is to be able to solve multi-step linear inequalities in two variables, algebraically and graphically. Let's take a look at this situation. You have two summer jobs at a youth center. You earn $8 per hour teaching basketball and $10 per hour teaching swimming. Your goal is to earn at least $200 per week. What is a possible combination of hours that will allow you to meet your goal? Notice this question is asking us to find an amount of hours. That is the thing we do not know but want to know. Notice that we have two different types of activities that are happening per hour. We earn $8 per hour teaching basketball and $10 per hour teaching swimming. So if there's two types of hours, that's going to cause us to use two variables. $8 per basketball hour. Remember, the per is like when we say times X, where the number of hours teaching basketball is the X, and $10 per hour teaching swimming, where the swimming would be the other variable like Y. So per hour swimming would be like times Y. So we have 8x and 10y, and then notice the keyword at least 200. At least means it can be 200 and more, so greater than or equal to 200. So the way we finish this is greater than or equal to 200. Now, how do we solve this inequality? We haven't yet encountered an inequality with two variables. This requires solving by graphing in many cases. And remember, when we graph equations in two variables, we can use standard form like ax plus by equals c and use the intercepts, or y equals mx plus b. So how is solving by graphing when it's two variables going to look different? Let's take a look. Notice these examples down here at the bottom. The shaded region shows all the points that are solutions of the given inequality. Notice that all of these are set up like y equals mx plus b. Of course, there's a less than or greater than symbol instead of an equals. But let's write down to remind ourselves, this is just like y equals mx plus b. Now, how do we know what kind of line to draw? Well, notice the differences in these examples. When there is an equal sign, see the equal sign? That means the solutions can happen right on the line. It's like the equal sign in y equals mx plus b. So whereas when we have an equal sign, we normally graph a solid line. That's what we do when we see the equal sign in a greater than or less than inequality. We graph a solid line. When it's not equals, see I don't have the line under, then we graphed a dashed line because none of the solutions can equal the points on the line. And then, because we start with y, and y goes up and down, so because we have y equals and y goes up and down, we have to look at the less than or the greater than symbol to know if it's up or down. If it says y is less than means numbers smaller, and numbers smaller means shade down. So notice that all of the points will be solutions that are down from the line. Here's another less than. That also means down from the line. All of these points are solutions of the inequality. If it's greater than means up. So from the line and going up, all of these are solutions to this inequality. And here, greater than means up because y is up and down. So all of these are solutions of that inequality. So let's fill out this chart and read what we have here just to clarify and take a good note. Graphs of linear inequalities include the graph of a line and a shaded region. The line can be solid or dashed. The shading can be up or down. So remember, how do we know when it's solid line or a dashed line? It's all about the equals. If we see an equals, then the line is solid. If we see equal, the line is solid. If we don't see the equals, the line is dashed, like this. Here, I don't see an equals, the line is dashed. Then, the less than or greater than tells us which way to go. This is less than, and less than means shade down. Also, less than, that means down. Greater, this is greater than is shade up. Also a greater than shades up. Let's practice some. Graph each inequality. So notice this is already set up like y equals mx plus b. Remember that b is where we begin. So first we look at the beginning point, the y-intercept. B is 3, so on the y-axis from the origin 1, 2, 3. There is where we begin. Then we move with the slope. So move with m. M is -2, make it a fraction, over 1 so that we know how to move. From our starting point, down 2 to the right 1, down 2 to the right 1. Continue to do that until we run out of room. Now we want to notice that we have a less than symbol. There is no equals here. So when it's no equals, we know we make a dashed line. So I'm going to find my straight edge, and I'm going to connect these points with a dashed line. At the end, I still want arrows to show it would keep going. Then I see that this is a less than symbol. Less than means shade down. So I put my pencil somewhere on the line and I indicate going down. I'm going to go below this line. So all of these are points that are solutions of the inequality. Well, an easier way to do this than to draw all the points is just to shade this region that is below the line. All of these are points that are solutions of the inequality. Notice number 2 is in standard form. This is like ax plus by equals c. And the first thing I try to do when I see standard form is use intercepts. So I'm going to try to use intercepts before I try to change it into y equals mx plus b. So let's find the x-intercept, cover up the y, and we see 2x equals 10. Divide by 2. So x equals 5. The x-intercept is 5, 0. On the x-axis, 1, 2, 3, 4, 5. Now let's do the y-intercept. Cover up the x, and I see what's left over. Negative 5y equals 10. Negative 5y equals 10. Divide both sides by negative 5. And y equals -2. 0, -2 is the y-intercept. So on the that's +2. On the y-axis, down 2. Now I need to think of how do I draw my line. Well, notice I have an equal symbol right here. That equal symbol tells me to make a solid line. So I get my straight edge and I connect my points with a solid line. Put arrows. Now I need to know which way to shade. So I see that I have less than. This is a less than symbol, so it means shade down. Down when it's a less than symbol. But notice that in front of the y, when we would get y by itself, there's a negative. The opposite of y means do the opposite of what's here. So flip that around to greater than, which means shade up. So anywhere from this line, I want to shade up. So anywhere that is above this line is where I'm going to shade. So all of these are points that are solutions. Let's just go ahead and shade in that region with our pencil to show that all of these are solutions of the inequality. They satisfy the inequality. Examples. Do the solutions satisfy the inequality? Remember that satisfy means to make true. It will make the inequality true. So in number 3, the inequality is y is less than negative 2x plus 3. Let's see if this ordered pair of x and y make this inequality true. So where I have y, I plug negative 8, less than negative 2. Where I have x, I plug 4, and then plus 3 is at the end. Negative 2 times 4 is negative 8, and negative 8 plus 3 is negative 5. Well, negative 8 is less than negative 5. This is a true statement. So does this solution satisfy the inequality? Yes, this is a solution because it satisfies the inequality. Now notice that this is the inequality that we graphed in number 1. Let's take a look at the point 4, negative 8 and see where it is in that graph. So from the origin, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, it's going to be down here in this shaded region. And remember we said that all the points in the shaded region are solutions. They satisfy the inequality. Well, that's a graphical way to tell. What about 0, 3? Let's go back and look at the graph. 0, 1, 2, 3. Well, it's in the green part, but it's on a dashed line. And the dashed line means not solutions. Let's go take a look at what it looks like when we plug this ordered pair of x, y into our inequality. 3 is the y, so I put 3 less than negative 2, 0 is the x, plus 3. 3 is less than 0 plus 3, and 3 is less than 3. Well, this doesn't say less than or equal to, it just says less than, and 3 is not less than 3, so this is not true. So does this solution satisfy? No, this is not a solution. It does not satisfy the inequality. How about number 4? This was the one we graphed in standard form. Let's take this ordered pair and plug it in. X is 3, so 2 times 3 minus 5 times the y is negative 2, less than or equal to 10. 2 times 3 is 6, plus 10, less than or equal to 16. 6 plus 10 is 16, less than or equal to 10. 16 is not less than or equal to 10. This is not true. So this solution, or no rather, this is not a solution. It does not satisfy the inequality. How about the second point? This is x and this is y. Let's plug it in. 2 times 10 minus 5 times 2 less than or equal to 10. 20 minus 10 less than or equal to 10, and 10 is less than or equal to 10. Well, this time there is an equal, and 10 is equal to 10, so this one is true. So yes, this is a solution. It does satisfy the inequality. Finally, let's revisit that situation we began with. So remember, you earn $8 per hour teaching basketball. Basketball is our x, so we have 8 times x, and $10 per hour teaching swimming. Swimming is our other activity, so that will be y. So plus 10y, and then the keyword at least means greater than or equal to $200. So greater than or equal to $200 is our inequality. What is a possible combination of hours? That's what we're looking for, how many hours, that will allow you to meet your goal. So notice we can graph this inequality as I've done for you in this picture. Standard form, remember, helps us to find intercepts. So if I'm going to use the intercepts, 8x equals 200 gives us x equals 25, so 250 is one of the intercepts as it shows. And then the y-intercept, 10y equals 200, and y equals 20, so 0, 20 is our y-intercept as it shows. And then we connect those points with our solid line because we have the equals. How do we know where to shade? This is greater than, so it's everything shaded above the line. All of these points are solutions that satisfy the inequality. Notice this point that I showed you right here. That's not in the shaded region. What this is an example of is not a solution. If 5 is x and 5 is y, that means 5 hours teaching basketball and 5 hours teaching swimming. So the x is the 5, the y is the 5. Let's look what happens when I plug it into the inequality. 8 times 5 plus 10 times 5 greater than or equal to 200. 8 times 5 is 40, this is 50, and 40 plus 50 is 90. Is 90 greater than or equal to 200? No, this is not true. So is 5 hours teaching basketball and 5 hours teaching swimming a possible combination? No, this is not a possible combination. Combination is when we put things together. It's not a possible combination of hours. Can we use the graph to figure out what would be a possible combination? Well, anything in the shaded region would be. So if I pick 10 for the x and 15 for the y, that's in the shaded region. X could be 10 and y could be 15. So that would be 10 hours of teaching basketball and 15 hours of teaching swimming. And that would be a possible combination. We can plug it in to the inequality to check another way. 8 times 10 plus 10 times 15 greater than or equal to 200. 8 times 10 is 80, 10 times 15, 150, and adding those together makes 230. 230 is greater than or equal to 200. This is true. So this is a possible combination. Can you think of another possible combination that would work? I bet you can think of many. Take a couple minutes to write a short summary. Explain how you know whether to shade up or down given an inequality in two variables. See you in class.